Hey, my name is Parth Patel, and I went to the public lecture on forecasting turbulence on November 26th. The lecture was given by Michael Schatz, or Professor Schatz, and basically the lecture was about fluid turbulence and how it's one of the greatest unsolved problems of classical physics and the subject of the $1 million mathematical challenge. So basically, even through centuries of research, there's been lots of different efforts by lots of famous physicists who have failed basically to yield some sort of like tractable or predictable theory for turbulence. But recently, there have been some computational advances that have allowed successful linkage with certain patterns within turbulence to sort of like solutions to equations that like govern fluid flow, like Navier-Stokes and whatnot. Uh, but obviously, the solutions still aren't robust enough to be able to predict everything. So one of the biggest things is like proving these these different theories and equations experimentally. So that's what the professor gave in the lecture. He's actually working on that, is proving these things through experimentation. Uh, where the geometry of key coherent structures is identified and harnessed to construct a roadmap to forecast the behavior of weakly turbulent flows. So that's just like an intro to the um, to the public lecture, and then and some of the main points essentially of the public lecture as well. So why this topic was also pretty interesting to me because it was basically like there's a reason for everything. So essentially, you have turbulence, which is completely unpredictable. It could be, you know, so going all sorts of different ways. But eventually, you're going to be able to find some pattern, and that's what I find really cool. And something that the professor presented that I found something interesting and I learned from was deterministic chaos. So, like for example, chaos or like butterfly effect is just random things happening all over the place. But if you follow it long enough, you can find some sort of pattern. Sort of like if you use a neural network and like apply it, then a neural network will be able to find whatever pattern you're looking for, right? Which is pretty cool. Um, and some of the other things that I thought were pretty cool is that like how this type of research can be applied to like your blood flow and knowing how your blood is moving, or being able to get certain like clinical data or metrics from that, or how certain like turbulent blood flow could be related to stroke or other health issues, or looking at your tissues and how that's affected, because there's so many other things going on in your body that there's no way to accurately predict like, oh, this is where your blood flow is, because there's so many things affecting it. And so if you could come up with an equation that basically explains that, then that would be huge. So measuring 3D turbulence I thought was also like really interesting and pretty cool. And then another thing was that like, why has the $1 million question not been answered yet, essentially? And that kind of goes back to what I was saying before. Um, and in the lecture, professor was saying that like experimentally we haven't been able to prove it, um, and that the question hasn't been answered because of that. And, certain equations just can't explain it. Well, I also think that another reason why that it hasn't been answered yet is because that we're missing something computationally. So like maybe there's a wrong assumption, or maybe there's something that we're basing turbulence off of that's not right, or maybe experimentally we just can't recreate the right conditions to prove certain things, right? Because even experimentally it's hard to control everything, so you only know one factor is changing. And with turbulence, it's all over the place and in all 3 dimensions and everything like that, which is pretty crazy. But yeah, that's basically a gist of what the lecture is about. It's pretty interesting, forecasting turbulence and being able to predict that. If we can accomplish that, it'd be pretty cool, and there could be a lot of different applications to it, which would be really interesting. And yeah, thanks.